Hello and welcome. I'm Greg Johnston. I'm a Senior Application Specialist with Sensors and Software. The topic today is part 2 of using the LineView module, which is part of the EKKO Project GPR analysis software. LineView is the software we use for plotting GPR lines, also known as GPR cross-sections. Part 1 of this webinar showed the basics of how to use LineView to plot GPR lines. In this webinar, I'm going to show you how to use the more advanced features of LineView. This webinar assumes that you've seen part 1 and know how to plot a GPR line and apply the simple numbered gains. If you've not seen part 1, it is available on the Sensors and Software website or the Sensors and Software YouTube channel. One housekeeping item. During the webinar, I have everyone muted, but you can type questions at any time, and I will answer those during the question and answer session at the end. Okay, let's dive in. Here is the main screen of EKKO Project. Hopefully you've seen my other webinars about how to open GPR data in EKKO Project and the function of all the windows in EKKO Project. My data was saved as a project file with a .gpz extension, so I'm going to browse and open it. Okay, hopefully this is all very familiar territory for you. The main function of this webinar is talking about LineView, so I'm going to get right into LineView. I'm going to select all the GPR lines in the Project Explorer window. So I do that by clicking on the folder, it selects all of them, and now I click on the LineView button on the toolbar. There we go, there's LineView opened up, and all the lines are open, so I'm going to tile them and put them on the screen. As I showed you in part 1, when you have a GPR line displayed, it can be modified in various ways using the View Settings menu. Either here, I can either go to View Settings and select that, or I can click on the View Settings button on the toolbar. This is the button with the red, green, and blue sliders. And this opens up the view settings. There's a dialog with several tabs visible. We have the General tab, Color Palette, Gain Filter, Axes, Limits, and the Legend. In part 1, we learned to use the basic feature of these tabs, including interpolation in the General tab, color palettes in the Color Palette tab, the depth axis in the Axes tab, and modifying the legend in the Legend tab. As a bit of a review from part 1, in my current situation, I see that when I tiled the GPR lines, the GPR data images are tiny compared to the legend under the image. You can see this in the background, that my legend on each of these images is taking up a lot of real estate, and so I really can't see the GPR sections very well at all. So what I might want to do is turn off the legend. Now I can do this one at a time by clicking on the window and then clicking on the legend button on the toolbar. But a more efficient way of doing that is to actually go into the Legend tab, unclick the Show Legend button, and then in the bottom here, click on Apply to All Open Lines. When I click there and hit OK, it's going to close the legend on all the windows. There, now I can see, they're small, but I can see the GPR sections much better. Now that I have all the GPR lines tiled and as big as possible, let's look at some of the view settings features we skipped over in part 1. You will recall that the General tab under View Settings controls how the GPR line is displayed. Typically, we check this button here, which is called Color Scale, and that's usually how we look at the data. And we add interpolation to it. But I would like to discuss wiggle traces, which is another way of plotting GPR data traces. If I open up one of these lines larger. Okay, so again, in the General tab, we want to have a wiggle trace plot. So I'm going to check the wiggle trace, and I'm going to uncheck the color scale, and I'm going to hit OK. And what you see is this data section is now plotted with wiggle traces. Now, depending on the screen resolution, the wiggle traces may be hard to see. So let me use the zoom box to zoom in. I'm going to do a couple things here. I want to change the color. So I'm going to go back in here. Let me change the color of the wiggle traces from blue to black, which is a more traditional color. And I'm also going to zoom in. So I want to zoom in so you can really see what wiggle traces are. So you draw a box, and we zoom in, and you can see the wiggles close up. And you can see how the stronger signals produce a larger deflection in the wiggle trace. The better way to look at wiggle trace plots is to add shading to either the positive or negative part of the GPR signal. The shading can be none, left, or right. So let me open that one up. So I'm going to change from no shading to shading on the right side, which would be the positive part of the trace. Okay, so now you see the traces, the wiggle traces, with the shading on that side. It makes it a lot easier to look at. And if I click on looking at the full screen, you can see what it looks like. Wiggle trace plots are how old-timers like me plotted GPR data in the early days of the technology, when all you had was a monochrome screen and a black and white printer. GPR data is not typically plotted like this anymore, but there are a surprising number of people who still prefer this type of plot, especially geologists, geomorphologists, and sedimentologists. So it's available in LineView. In fact, years ago, we took it out of one of our software packages, and we immediately got complaints from customers who like to plot their data in wiggle trace. So we put it back in. Now, I want you to note that you can create some interesting plots of GPR data by combining wiggle trace and color scale together. Let me show you. So for example, let me remove the shading. I'm going to get rid of the shading. I'm going to go to color palette. And I'm going to switch to the seismic color palette, and I'm going to hit OK. This is kind of an interesting looking image that combines both the color scale and the wiggle trace. And again, if I zoom in, you can see that effect of both the wiggle traces and the color scale. Okay, let me get this back to a more typical plot. Again, I go back into here and I go to color scale, and I'm going to turn off the wiggle trace. And I'm a big fan of the grayscale color palette, so I'm going to hit the default and go to that one as well. So here we go, back to a plot that I'm more used to looking at. All right, now let's jump over to the Gain and Filter tab. This is not a tab I discussed at all in part one of the webinar, of this LineView webinar. Now, looking at this is one of the most intimidating dialog boxes in the EKKO Project software. But let me show you what it does. The Gain Filter tab controls the processing applied to the GPR lines, specifically the gain and the filter processing applied. Now, we suggest that novices plot their GPR data with processing based on the recommended processing button. This button right here, if you wander in here and don't really know what it's doing, click on the recommended gain and filter, and it will set you up with an auto gain and the default filtering. Now, this will set the Dewow filter on, and as I mentioned, the gain to auto gain. Most of the time, the recommended processing will make the GPR cross-section look good. But let's dig a little deeper into this dialog so we have a better understanding of the processing for the times that we want to do something a little different. First, notice the process called Dewow is always checked on. What does Dewow do? It removes wow, of course. All GPR data has a low frequency component in it called wow. This is slowly decaying low frequency signal that may be induced onto the GPR trace due to a combination of how close the GPR transmitter and the receiver are from one another and the electrical properties of the ground. If you have a bistatic GPR system like the pulse echo, collect some data traces with the transmitter and receiver closer together than recommended, and you will really see wow. Now let me open up a new section here. Here is a GPR line showing limestone geology from an abandoned limestone quarry. You can actually see some bedding planes running through here in this direction. There's ringing responses here from metal left over from the days that it was a quarry. And we actually get some responses from caves over here. Here and here actually have been confirmed to be caves. They drilled those to confirm that. Now let's look at this GPR line with the wow left in it. I do this by turning off the Dewow. When I do that and I hit preview, look at this. So that's what wow looks like on the GPR line. Quite different, isn't it? Let's look at it on the GPR trace level. This box here shows the GPR traces, which changes as I move my mouse cursor across the GPR line. Notice how the GPR signal near the top does not oscillate around 0. I'm looking up in this section in here. It's not oscillating around 0. It's offset to the right of 0. This is the low frequency wow that I was talking about. By applying Dewow, we remove that wow, the low frequency component, so the signal oscillates around 0 and looks much better. So if I turn Dewow on and I hit preview, this is what we're used to looking at. Technically, Dewow is a high-pass temporal filter. What that means is that it lets the high frequencies pass through the filter unchanged, but it does not allow the low frequencies to pass. They are removed. So in 99.9% of cases, you will need to apply the Dewow filter for your data to display properly. This is why we default it to on, and you have to consciously turn it off if you don't want it. If you collect a lot of data with different antenna frequencies, you'll notice that low frequency antennas from 12.5 megahertz to 200 megahertz tend to have more wow than higher frequency antennas from 250 to 1000 megahertz. For example, let me open up some 500 megahertz data here. So this is 500 megahertz data. Let me turn off the Dewow here and look at the effect. There's not an enormous change. So if I play this back and forth, so this is the wow left in it and with the Dewow. So not a huge change. There's only a very little bit of wow in the high frequency data. Again, we tend to see wow more in the low frequency data. As a GPR user, it's important to have at least a basic understanding of wow and the Dewow filter, because data plotted with the low frequency wow left in often looks like the depth of penetration is greater than it actually is. Over the years, we've seen dishonest or ignorant people show GPR data with the wow left in and claim that their GPR system can penetrate deeper than is possible given the physics. The lesson is to be skeptical of any GPR data that seems too good to be true. Okay, let's stay in the gain and filter tab here. Jump back to my PowerPoint. And I want to discuss gain. In part 1, we discussed why you need to gain GPR data. Remember this slide. GPR signals get weaker as they travel deeper into the subsurface because of attenuation. So to see them in our GPR line plot, we need to apply a gain with a ramp, where there is less amplification on the top where the GPR signals are strong, and more amplification at depth where the signals are weaker. In part 1 of this webinar, I showed you the auto gain and using numbered gains to change the gain applied to the GPR line. There are very simple ways of changing the gain. These buttons here, you remember, are the gain buttons. Right now it's using an auto gain. I can use the drop down to change it to a numbered gain, and then I can click on the plus buttons to amplify the signal, more and more gain, or I can click on the minus buttons to reduce the gain. We also talked about over-gaining the data, under-gaining the data. Hopefully you recall all that. But here's what happens sometimes. Sometimes with the numbered gains, what happens is you want to gain between two of the numbered gains. For example, a gain of 6 is not enough gain, and a gain of 7 is too much gain. Let me show you how to adjust the gain between two numbered gains. So I'm going to select a utility line. And so right now this is the auto gain, and I'm going to zoom in, and I'm going to scroll over to the first part, and here we see a bunch of utilities, right? That was the main targets in this. The auto gain isn't bad, but I would like to add a bit more gain. So I go to the numbered gains. Here's a gain of 1, that's a bit low, 2, 3, 4, 5. And what I find is that here's 6 and here's 7. And I may look at it and go, well, you know what? 6 isn't quite enough and 7 is too much. I want to gain it in between those two values. So how do I do that? This is what I'm going to show you right now. So I go to the View Settings button. I go to the Filter, the Gain Filter tab. And now I'm going to talk about the gain that's here. You'll notice that the gain type is set to SEC2 gain. And we're going to talk more about gain types in a few minutes. That is our default gain, is SEC2. And you see the level is 6, and that's the one that corresponds to the level that I was using on the toolbar. Now there are 3 parameters that control this gain function. An SEC gain is a ramp-like gain. It starts off small and it goes more amplification as the depth increases. So let's have a look at those 3 parameters. And I've got a PowerPoint slide that shows this. So these are the 3 parameters off to the side. We've got a GPR section in the middle, and we have the 3 parameters off to the side. The start gain is the amount of gain right at the top of the GPR line. It's often set to 1, which means that the raw signal is not being amplified. But sometimes you may want to apply a little amplification to the signal right at the top. The second parameter is called attenuation, and this value controls how steep this ramp is, meaning how quickly the gain increases. The higher the attenuation value, the steeper the ramp. You see here attenuation of 0.5 is a very gradual ramp, 1 is a steeper ramp, 5 is an even steeper ramp. This parameter tends to affect the gain in the mid-depths of the GPR line. The last parameter is the maximum gain. This is the maximum value that the weakest signals in the bottom of the GPR line will be amplified. It tends to affect the gain at the bottom of the GPR line. So let me go back to my data here. Let's look at these parameters for this GPR utility line. At a gain level of 6, notice that the start gain is 3.5, the attenuation is 4, and the maximum gain is 500. We can plot what this gain looks like in this dialog. In the same box we looked at the effect of turning Dewow off, we can plot the shape of the gain. Let me do that by unchecking the raw, checking gain, and unchecking the processed. So the only thing in this box right now is the gain function. So we see that It starts at 3.5, it increases gradually, and it peaks at 500, and then it flattens out at that point. I can display exactly what gain is applied at each depth in the GPR line. I do this by moving my mouse cursor up and down on the GPR line. You can see, hopefully you have enough resolution to see a horizontal black dashed line visible in the blue gain box here. And that corresponds to the current depth of my mouse cursor on the GPR line. For example, if I move my mouse cursor to the top of the section, the value listed beside the word gain here is 3.5, which is exactly the start gain value, and that's exactly what we expected. If I move down to a level about here, the gain is about 40 times. And if I move my mouse cursor right to the bottom of the image, the gain is 500 times. If we use the gain level drop-down to change to level 7, so I'm going to switch from level 6 to level 7, and I hit preview. Now I have a new gain. Now I'm looking at the level 7 gain. The start gain is higher at 4, the attenuation is higher at 6, and the maximum gain is the same at 500. When we look at the gain plot, we now see that the ramp at gain level 7 is steeper than the ramp at gain level 6. It hits the maximum gain of 500 well before the bottom of the GPR line. Again, our goal here is to apply a gain between gain levels 6 and 7. To do this, the first step is to change the attenuation, that is the steepness of the ramp. I want to change it to a value between the attenuation at gain level 6 and the attenuation at gain level 7. Now recall that the attenuation at gain level 6 was 4, and the attenuation at gain level 7 is 6. So we're going to try an attenuation value right in the middle. We're going to pick a value of 5. So I can either use the drop down to select a value, or I can type the value in and then I hit the enter key. And then when I hit preview, it will update with the new gain. So you can see the difference. Let me go back. So if I use an attenuation of 6, enter, and I hit preview. So compare that gain to changing it to 5 and hitting preview. So watch the change here. So it's a slight change, but that's what it is. We're in between two of the numbered gain values, so we don't expect it to be a large change. Okay, if you're still not happy with the gain, you can change the other values. Change the attenuation value or one of the other values. For example, let's go with the new attenuation value of 5, but let's change the start from 4 to 2. We change that to 2. And hit preview. Now you can see that had a large effect. That really dulled it, ungained, or it lowered the gain in the top part of the section. And in fact, it actually does a really nice job of emphasizing these hyperbolic responses from utilities. So I think it actually did a pretty good job, that little tweak that I did to the gain. So now these three parameters, the start gain, the attenuation, and the maximum gain are what controls the gain. And now you know how to modify them to get the perfect gain for your GPR line. Remember, it might take a few minutes of experimenting with different numbers to get the gain that you're happy with. An SEC gain is not the only type of gain, and other types of gains have their place. Let's look at some of the other gains. In the same gain filter tab, go to the gain type dropdown and select none. So I'm going to select none and I'm going to hit OK. This removes all the gain, so none is applied to the data. In this particular GPR line, no gain is not really that appropriate, although I am kind of surprised. Look at this utility here at about 32 meters. This is visible with no gain. in the data, which kind of amazes me. Now, there are situations when you might want to apply no gain. And these are going to be situations like if you collected data on ice, it typically doesn't need much gain. Concrete data doesn't need much gain to see the reinforcement. Or just in areas where there's very little attenuation to the signal. Let's look at a geologic section and have a look at it with no gain. So again, let me go back into here, go to the gain filter, go to the gain type and change it to none. And if I look at this section with no gain, you can see that we do see some signal. And it amazes me that this reflector, 22 meters in depth, is so strong that we can see it with no gain. Plotting your data with no gain is a great way of displaying the strongest reflectors in your data, which is knowledge that helps you when you're interpreting the data. Now, another type of gain is called automatic gain control, or AGC. This type of gain automatically adjusts to the strength of the signal. In other words, where the GPR signal is strong, it applies a low gain. And where the GPR signal is weak, it applies a high gain. So let's look at this one with an AGC gain. So again, I go into View Settings, Gain Filter tab, go to the gain type, change it to AGC, and I hit OK. Now you can really see the effect of this gain. It's a great gain. AGC is a great gain for out in the field because it boosts up all the signals so it's easy to see. So you can tell if you're getting good penetration and having a successful GPR survey. The bad thing about AGC is that it amplifies the weak and the strong signal to the same level. So there's no longer the possibility of comparing signal strength. Now, there are numbered gains for all the different gain types. What this means is that after you change the gain type in the Gain Filter tab, you can press OK and close the View Settings dialog. Now you can use the gain buttons on the LineView toolbar to modify the gain. For example, if I take this AGC gain down to AGC number 1, this is what it looks like. Here's number 2, and we can see it applying more and more gain as the numbers get higher. So you can see by the time we get to a level 6, even these very, very weak signals from depth are all amplified very strongly. Now, if you're only interested in the geometry of the reflectors, AGC may be a good gain to use on your data. It's often used for geologic data. But let me show you why we don't recommend this gain for utility locators. Let me go back to this line with our utilities, and let's plot it. Right now it's plotted with no gain. So let me change the gain type to AGC. And here you go. The nice hyperbolas from utilities that are visible in the SEC gain kind of get buried in all the signal with the AGC gain. Now let me back off the AGC gain a little bit. Let me take it down to 1. And you'll see, okay, it starts off not bad. AGC of 2 or 3, this isn't too bad, but some of these shallower hyperbolic responses are starting to get buried, starting to get overwhelmed by the other signals around them. So when you're looking for point targets like utilities, it's not a good thing to amplify all the weaker signals because the utility responses get lost in the other signals and the interpretation is much harder. The next type of gain is called constant, which is pretty easy to understand because you're just applying a constant amplifier to the signal. So if I switch to constant and I say OK, this is what we got. So it actually looks fairly similar here. So here's constant gain. Let me take this up a little bit to say this level. There. Now, what we tend to see with a constant gain is that it tends to overgain in the shallow part of the section and undergain in the deeper part of the section. Now, if you look at the gain type list, there's one more type of gain in here. It's called DVL gain. I'm going to leave that one for you guys to explore. Now that you know how to change gains, I'm going to let you experiment with that one. Okay, so I'm going back to my SEC gain, which is the default and the one we generally recommend. Okay, so now open up View Settings again. Now let's move to the Axis tab and finish some business there. In part one of the LineView webinar, we discussed most of the features of this tab, including reversing the line direction so you can plot GPR lines collected in a zigzag fashion in the same direction. We also discussed displaying and modifying the position axis, the time axis, and the depth axis. But I'm sure many people were looking at the elevation axis checkbox and wondering, how can I have an elevation axis on my GPR line? That is what we're going to discuss now. Okay, now I need to open up a different set of data. Okay, having an elevation axis is handy because sometimes your GPR data is not collected on a flat area. For example, areas like this. Up a dune or up a hill, you're not collecting on a flat response. And sometimes that topography can affect how you interpret your GPR data. Now, unfortunately, the GPR system does not collect elevation data. Elevation data needs to come from some other source and added to the GPR data. I'm going to show you two ways of adding elevation data to your GPR line. The first is the easy lazy man's method, GPS. As you know, GPS is used to find your latitude and longitude and position you on the Earth. But GPS data also has the Z component, or the Z component, which is elevation. LineView uses the elevation component of the GPS signal and automatically applies it to the GPR line. Easy peasy. So anytime you collect your GPR data with GPS, you can plot your GPR line with an elevation axis rather than a depth axis. Let's have a look at this. So here's line 6 plotted in depth. Let me jump back here for a second. I do want to point out something here. You'll notice that beside the name line 6 in the Project Explorer box, there's a little G. And that little G means that this data was collected with GPS. And so we're going to take advantage of that by using it for the elevation. In this example, I'm first plotting the data with a depth axis. We have this strong sloping reflector that varies from about 4.5 meters deep here on the left to about 3 meters deep on the right. Now let's use the GPS elevation data value to plot the data with an elevation axis. So I go into View Settings, go to Axes, and I switch from depth to elevation, and I hit OK. So here's the data plotted with topography. So you'll notice the depth scale on the side on the left here is now switched to an elevation scale. And so the elevation of this particular data set was around 223 meters. We also see that the sloping reflector in the depth section is actually a flat line reflector, and it's the surface that's sloping. That information will likely change our interpretation of this reflector. In this case, this reflector is interpreted as the water table. It's visible in this case because the sediments are coarse, and therefore the water table is a sharp boundary, the type of boundary that GPR is good at imaging. Now, I know my audience is sharp, and a bunch of you are thinking right now, but the elevation is of the GPS receiver, not the ground. How do I subtract the height of the GPS above the surface so I actually plot the true elevation of the ground? Fear not, my audience, we have that sorted out. We simply exit LineView and go back to EKKO Project. We check the line that we're interested in, and then we go to the Tools, GPS menu. So I'm going to go to Tools, GPS, and I'm going to select Offset. And this little dialog opens up. And this allows me to offset the distance between the ground, where the GPR antennas are, and the GPS. We can do this in the X, Y, and the Z direction. In this particular case, our GPS was directly above the GPR. So our only concern is the height. So in this box under the Z value, I can put in 1.75 meters, which is the height off the ground, and it will correct the elevation for that. So then if I plot the sections, and I'm going to plot two. I made a copy of one so that we can see before and after. We're going to see that one of them is actually been corrected for the height of the antenna. So the original one was at around 223 meters, and now we see that that's gone down to 221 3/4 or so. And so we've corrected for that 1.75 meter offset, which is the height of the GPS receiver off the ground. Okay, one warning. GPS elevation values are typically not as accurate as the XY position. And all GPS data is affected by tree cover and tall buildings that restrict the number of satellites that contribute to accurate positioning. What this means is the following. So if I look at line 1 here, and I plot it in LineView, here's my line 1 plotted with the elevation. So let me go back to the original. So here's the depth section. So here's the depth section, which looks pretty normal. This is like 600 meters of data. And here it is plotted with an elevation scale. And remember, the elevation scale is based on GPS. So the GPS wasn't out that much. It's only a couple meters, but look at this. And this is very typical. So unless you have good GPS data, the elevation values may be pretty useless. Okay, let me show you a second way of adding elevation data to your GPR line. In fact, we have plotted data with topography using this same method since the 1980s. This is based on the idea that you got your elevation information from some other type of survey, perhaps an actual survey, topographic maps, or just eyeballing the elevation changes along the line and estimating them. What we do is create a text file that contains the elevation information at positions along the GPR line, and then we attach that to the GPR line. So the file is called a .top file, a topo file. Now let me show you how simple it is to create one. Say we have this line, this limestone data that we've been looking at a few times today, and say we want to add topography to that, so we can plot it with topography. So what I'm going to do is, first I'm going to create a topography file. This is independent of the data at this point. So I'm going to use NotePad to do this. So I'm going to right click and I'm going to create new, and I'm going to create a text file. When I go to a text file, it's going to create a new document. So I'm just going to click on that and it's going to open up in NotePad. Okay, so here we go, blank section of NotePad. So I'm going to create two columns. The first column is going to be position along the GPR line, and the second column is going to be the elevation. So I'm going to do a very simple topography file. At position 0 along my line, the elevation was 10 meters. By the time we got to 25 meters along the line, the elevation had decreased to 5 meters. When I reached 55 meters along the line, the elevation had decreased further to 3 meters. And by the time I got to 64 meters along the line, the elevation was 0. And so this was just eyeballing it. So all I've got is 4 points in this section. Now the key here is to not save this file as a text file, which is the default file extension of NotePad. Instead, go to Save As, go to the Save As type, and use the drop-down to select All Files. And now I can type in whatever extension I want. So I'm going to call this, the name of the file is rock100 is the name of my GPR line. So I'm going to call it rock100.top, which is the type of extension that I need. And I'm going to save that. So now I have a file called rock100.top. Now at this point, I want to attach it to the GPR line. The two of them are independent right now. So I'm going to go back into EKKO Project. Now I'm in LineView, so I'm going to click out of LineView and go back to EKKO Project. And I'm going to select that file name in Project Explorer, which was rock100. And I'm going to use the Attachments tab here. And I go to the Attachments tab, and one of the options is Add a File. And that's exactly what I want to do. So I click on the buttons here, and the file that I want to add is the topo file, the .top file. So I select that file, I hit Open. It gives me a warning, but it does do it. And now over here under the attachments, it now says that rock100.top has been attached, and it is a positioning file. And over here in Project Explorer, there's a little T beside the name, rock100, and that means that topography has been added and been attached to that file. So now that the GPR line has elevation information, now I can plot it with an elevation axis. So let me open it up in LineView, and I'll make it large. So right now it's being plotted as a depth section, but I go into the axes, and now I'm going to switch from depth to elevation, and I hit OK. So now here's the section plotted with elevation. Now, I made a copy of it. Let's look at both before and after. There's a copy of the data here. I have a second copy of it here. So now here's both of them. So we can see the original depth section over here, and then we can see once we've applied a very simple topography on it. So notice that some of the reflectors that look like they were dipping are actually closer to flat lying or just more gently dipping. So adding topo to your data can be a real benefit. Now I want you to note that I only had 4 values. I only had 4 elevation values in my .top file. You can have as few as 2 points and as many points as you want, whatever it takes to define the shape of the topography along the GPR line. Okay, now I want to talk about limits. And again, under View Settings, we're going to go to the Limits tab. Okay, now that we've added elevation data to this, the Limits tab is going to make more sense to you. The Limits tab is used to set limits on the top and bottom of the GPR line. This can be done in time, which is actually how GPR data is collected. It's collected in time. So it can be limited in time, it can be limited in depth, or limited in elevation. Now, in this case, the depth limits are grayed out, and they're not accessible because we're plotting the data with an elevation axis. If we switch to a depth axis, the elevation limits row would become inaccessible. Now, I think this particular line is plotted well, but say we wanted to cut off the bottom at -20 meters in the elevation. So what I would do is I'd go down to the elevation row here. I would set the bottom limit to -20 meters. And when I hit preview, you're going to see now the elevation axis ends at -20 meters, and it cuts off the data at that point. Now I'm going to switch lines here for a second and look at one that really needs limiting on it. Let me get rid of this. Let me make this larger. So here's a GPR line where the depth setting during data collection was much deeper than the actual depth of penetration. The depth of penetration is maybe 3 or 4 meters, but the depth scale goes down to about 9 meters. This is not a nice looking plot because the majority of it is just background radio frequency noise and airwaves. Now, to prove that, let's use the skills I taught earlier, manually modifying the gain parameters to really amplify the signals deeper down in the section, which I'm saying are noise and airwaves. First, I'm going to apply the highest numbered gain. So I'm going to switch from the auto gain. I'm going to apply a gain of 12 to really crank up the gain. Now, you can see that this is not enough gain to amplify the signal deep down. So I will need to increase the maximum gain parameter. So I go into the gain filter, and I'm going to increase the maximum gain from 1,000 to 5,000. Really going to crank up the gain on this. And I hit enter, and then I hit preview. So here it is with a gain, with my new modified gain, where I'm gaining the bottom part of the section 5,000 times to really bring up the signals. Now we can really see this random noise and the airwaves. But how do I confirm that some of these signals are airwaves? Well, you remember from earlier webinars, I do that by a velocity calibration. So I click on the hyperbola button. This hyperbola appears on the screen. I put it on one of these deeper hyperbolas. I expand it out to see what the velocity is. I fit the shape, and the velocity I get is 0.3 meters per nanosecond, which is the speed of light. This means that the object that caused this reflection was in a material with a speed of light. The only material that GPR signals travel the speed of light in is air. So this object was above ground and not in the subsurface, even though it looks like it is. So if this is new to you, see my webinar on interpreting GPR data. The point is, we probably don't want to display the noise and the airwaves in the image that we create. So we want to cut data off the bottom. So again, I go back into my view settings and the limits, and now I'm going to either do this in depth or in time. So a more appropriate depth here might be 3.5 meters. So let me use 3.5 and hit preview. You see there, now we're seeing much better. We're seeing the real GPR signals at the top of the section. I think it's still overgained, but we'll ignore that for right now. Now, I could also limit it in time. So I could go to this time row and say, okay, I'm going to cut it off at 65 nanoseconds. If I prove very similar sort of setting. Now, when I plot the data like this, there's no temptation to interpret those deeper signals as something in the subsurface. Now, in this time row, I want you to notice an option that may come in handy sometimes. That is plotting the GPR line from the minimum time rather than 0 time, which is the default. You see, it defaults to 0, but I'm going to set it to min, and I'm going to hit OK. All sensors and software GPR systems collect about 10% of the data before the GPR transmitter fires. This means that we collect some of the background noise before the GPR transmitter fires. We call that pre-time 0 time or negative time. If you look at the time scale here, the values are actually negative. And in this case, we have about 20 nanoseconds of signal that was collected before the transmitter fired at 0 time. Now, this signal is not very impressive because the negative time signal is not being gained with the SEC gain we're using. But if I switch to an AGC gain, it will become visible. So I click, I go to gain filter, and I change the gain type to AGC gain, and I hit OK. Now that amplifies all the signals, those weaker signals, before time 0, before the transmitter fires. And if we look at this in a full time window, let me take the other limits out to the maximum and say OK. What we discover by this is that these areas of noise bursts at the top that we see in our GPR section here and here and here actually started before the GPR transmitter fired. So this confirms that these noise bursts are definitely background signals and they're not part of the GPR signals. Now let me show you an example where plotting the negative time with an AGC gain is very valuable and it helps our interpretation. I'm going to open up this line and I'm going to let you have a look at this, and I'm going to apply a bit more gain to it so you can see it. But one of the things that should strike you right away is this section in here. Obviously, you're going to wonder about this signal in the middle that extends down to the bottom. Is this GPR signal? Does it indicate the presence of that buried treasure that I've spent my lifetime looking for? Before you spend too much time wondering about it, plot the negative time data and change the gain to AGC. Let's see what we get. So I go into here, I change to AGC, and I jump over to limits and I plot from the minimum and I hit OK. And this is what we've got. Clearly, the signal that we're seeing in the GPR section down below actually started before the GPR transmitter even fired. So that means it's in the background. It is background noise. And so we can ignore it. So unfortunately, no treasure today. Okay, new topic. Sometimes you may see things plotted on the bottom of your GPR line that you don't want in your plot. The two most common ones are flags and skip traces. So let me change to a new section here. Let me show you what I'm talking about here. Notice in the bottom, there's a red triangle labeled number 1 and another red triangle labeled number 2 down here on the bottom edge. Those are flags or fiducial marker. So a flag or a fiducial marker is added to the data by the operator during data acquisition by pressing the star button on the DVL. Flags are useful for recording significant landmarks or objects encountered during the survey. As you can see, flags are indicated by the red triangles on the bottom of the section. If you ever want to remove those from your plot so they don't detract from the image, here's what you do. Go to View, right to the bottom is the Show Hide menu. And this is where we can say, no, don't show me flags or fiducials. Let's turn that off, and those will disappear off your image. Also, if you ever want to edit flags, this could be done back in EKKO Project. So if I click on the name of the file, so this one here, and I right-click on it, there's a menu option in the right-click menu that says Edit Flags and Fiducials. And so I can go in here and I can edit the position and the comment. So for example, you may want to change number 1 here to indicate what the flag actually indicates, like maybe edge of concrete or something like that. Okay, so that's how to edit flags or fiducials. Okay, let's go to another section here with another type of thing that appears in the bottom part of the section. And these are skip traces. When you collect data too quickly for the odometer to keep up, traces are skipped. So in the bottom edge here, we see a few little red rectangles on the bottom. So what happens is the traces are not actually skipped, they're repeated. Now, in this case, there's only a few skips, so it really doesn't make much difference to our data at all. In cases where more than about 10% of your traces have been skipped, the data acquisition software will actually warn you and suggest that you recollect the line. So in this particular case, I only skipped a few. It's not that important, but I don't want them to appear in this nice image I'm trying to create. So again, I go in under View, Show Hide, and now I go down to Skip Traces and I say, don't show me those. I don't want to see those. So you can actually see from this Show Hide menu, there are a bunch of elements that you can choose to show or hide, but all of them are accessible in other places in LineView. For example, on the toolbar or in the View Settings dialog. Okay, the last thing I would like to show you today is the ability to link multiple GPR lines together. This is a very powerful feature, especially when you're interpreting parallel lines. Let me show you an example. Come out of here, go back to EKKO Project. I'm going to select to plot in LineView 4 lines that are parallel. These are actually the lines that are visible in map view here. So I select those, I hit LineView, and we open them up in LineView. Okay, I'm going to tile them. So there's the 4 of them. Now these are they're 500 megahertz parallel lines. They're collected from an archaeology survey, and they're about 73 meters long. So the first thing I'm going to do is figure out the best gain. So I'm going to make one of these larger, and I'm going to play around with the gain a bit. I'm not going to spend too long. I'm going to say, yeah, you know what, 8, not bad. Let's go with 8. Now, I look at this data and I see that there's constant bands, these horizontal bands, which if you've seen my other webinars, this is system noise. There must have been a cable loose or something like that. Something metal was being energized near the GPR system and turned into an antenna, and it creates these things. So perhaps the person who collected this may have had their GPS cable dangling near the antennas or something like that. So regardless, it is something that we want to eliminate. So I'm going to turn on the background subtraction filter, which I discussed in part 1 of the LineView. So that does an excellent job at removing these flat lying bands and shows me much better reflectors in the data. Okay, so once I'm happy with the gain and the background subtraction, I'm going to apply that to all the open lines. So I go back into here, I say apply to all open lines, I say okay. It's going to apply the same gain and the background subtraction to all 4 lines. Now I can tile it, and I've got all 4 of them. To link all the GPR lines together, I go to View, and then there's this long name called Link, View, Position, and Time Depth Ranges. So when I turn that on, that links all 4 of these images together. If I scroll one image, all the other images will scroll. So for example, if I hit the Zoom Plus and I zoom in on all of them. They all zoom in. And now that I'm zoomed in, if I scroll one of them, I scroll all 4 of them so that I get the same position range all the time. One of the things I often look for in parallel lines is if you see the same response on multiple lines. So here I'm looking at line 64 and I say, oh, there's a hyperbolic response here around 48 meters. And so I'm going to click on the zoom box and I'm going to draw a box around that object. So I click and drag a box, and now I have the same box on the other 3 lines. And so I can quickly see that this is a unique feature. It doesn't extend onto any of the adjacent lines. It's only visible on that one line. And so that's useful information for me. Now, if I press on the Fit to Window button, all 4 of them will fit back to the window, so all 73 meters is visible again. Now, again, I notice that there's this interesting feature at around 20 meters. There seems to be this sort of mound-like thing. So again, I'll use the box, the zoom box, and I'll draw a box around that mound on the one, and it will zoom in on all 4. So on all 4 of them, I can see, oh yeah, there's this same mound. So that's visible on all these adjacent lines. So as an archaeologist, this of course interests me a great deal. So I want to note that you can use this feature as you add interpretations to your GPR lines. For example, if I now create an interpretation, new interpretation, I'm going to create a box interpretation called mound. Don't know if it's an archaeological term, but I'll go with it. So if I now create the mound interpretation and I draw a box around each of the mounds in the cross sections, now I can quickly go from one to the other and I can draw them. And now when I exit out of LineView and I go back to EKKO Project, in map view, I'm going to see that interpretation on those 4 parallel lines. So those blue boxes that I drew are now, you can see the spatial relationship of them. They're all visible here in map view. So I think you'll agree that linking GPR lines like this and zooming and scrolling through them and adding interpretations is a great way of reviewing and interpreting your data. So I will say that that is it for today. So we discussed some of the more advanced features of the LineView module in the EKKO Project software. Now, as I always say, the best way to learn software is to use it. So I encourage you to try and practice with LineView as soon as possible and practice the things we talked about today. If you do not have a copy of EKKO Project, we can send you a demo version to try. Just send an email to the address on the screen. So now I will answer the questions that you have submitted during the webinar. Does gain increase the depth of penetration, or is it only for visualization? It is only for visualization. Gain is only taking the signal that's actually there and amplifying it. It's just like turning up the volume knob on your car radio or something. The signal has a certain strength to it, and it's taking that signal and amplifying it. So that's all gain is doing. Gain does not actually go into the transmitter and send more power into the ground. Okay, so it's strictly visualization. Okay, under the gain tab, can you explain DynaT? DynaT is a feature that allows you to emphasize small, medium, or large objects in your data. So let me find a data set here. And if I go in under gain filter, there's this one called DynaT. So DynaT defaults to all. And so if you're interested in trying to emphasize in the data small, medium, or large objects, you can switch to one of these. So for example, if I set it to small and I hit preview, then it filters the data such that it's emphasizing the reflections from smaller features. If I go to large and I hit preview, now we're getting the response from more of the larger features. We're getting more of an emphasis on that. And if I compare that to all, if I go back to all, which combines all of them, you can see the difference. So it is a filter. Does elevation consider off-nadir look angle of the antennas? No, it doesn't. Not quite that clever at this point. The position of the trace is actually just moved up or down in it. So it's a very simple correction. Doesn't take into account the beam direction and that sort of thing. And you're absolutely right. You say on a slope, the antennas will be tilted and the GPS position will be shifted. Yes, that's all true. So we do not take that into consideration. But in actual fact, if you look at the geometry, a lot of times that angle is pretty small angle, so it doesn't affect it that much. Is it a problem to use the background removal in elevated data? No, because we actually apply the background subtraction we apply before we do the elevation correction. So you're actually applying the background subtraction filter is being applied on a depth section, and then we change it for the topography shape. Metallic artifacts deeply buried or locates in walls won't produce ringy responses anymore. So how can we find them? What I would be more likely to do is actually turn the gain off. I think what you're getting at is we know that metallic objects give you 100% reflection coefficient. So a metal object should give you the strongest response of any object in the subsurface. And so to try to recognize that, as you say that a metal object that's very shallow will ring. We'll get that ringy response, which you've seen before, hopefully. As it gets deeper, it gets more difficult to make it ring. And so you don't see that. So the only way that you can tell or have a chance of telling that it's a metallic object is through the amplitude. And so what you're looking for are the highest amplitude. So one of the things I do when I'm looking for this sort of thing is I'll turn the gain completely off. And if I need to apply any gain to see something, I will apply a constant gain. And so if I show it here, again, I'm going to go in here, I'm going to change to a constant gain. And let me change it to a very low gain of, say, 5. Okay. And so now what jumps out at me are with this very low level of gain. So at this whole level, in this entire level down here at about 40 nanoseconds or 2 meters, I don't see anything except these two hyperbolic responses from utilities. So I know that those represent the strongest reflections. I mean, the attenuation being equal. This is one of the things. If attenuation is varying, that's not quite the case. But if we assume that the attenuation is generally the same across the whole section, I know immediately that these two objects here represent the strongest reflection. And I actually just spotted another one. There's another one down here. And so if I have to start making guesses about composition and maybe metal, this is what I'm going to look for. So I'm hoping that answered your question. Thank you for attending today's webinar. I hope you got something out of it. And watch your email for the next webinar. And of course, please submit webinar topics that you'd like to see me cover in the future. So thank you. Have a good day.